I'm Kristof Van Tomme, and welcome to the API Resilience podcast. If you've ever wondered what it really is we do when we do APIs, and if you've wondered how APIs change organizations, our communities, and our society, look no further. This is the podcast you've been searching for.
Our guest today is Barry O'Reilly. Barry is a certified architect with global experience and reach, has background in Azure, service orientation, and IoT. He has many experience in building and leading teams, and is a community and thought leader within architecture. Barry is a regular speaker at conferences and events, and delivers world-class architecture consulting and leadership, coaching, mentoring, and teaching. In addition, he is the founder of Black Tulip Technology and creator of anti-fragile system design and residuality theory, aiming to redefine architecture as the management of complexity. And one more important detail, Barry is a PhD student in complexity science and software design.
Welcome very, very much, Barry O'Reilly. I'm really excited to have you as a guest finally, because I got really excited last year about the residuality theory that you've been promoting left and right. And I just heard how things are really, really booming and how everybody now wants to hear about this. Yeah. So for people listening here, if you want to invite Barry, you'll have to be quick because he's about to publish his book, and then it's going to get really hard to get him. Okay. But in all seriousness, I'm really excited about this because there's some of these frameworks that kind of like give you like a new leverage to think about the world. And I think residuality theory is one of these. And one of these that is really important in our industry, in the API industry, because we're in the middle of all these complex systems where creating resilient infrastructure is essential. And basically, residuality theory gives you a tool to create more resilient infrastructure and to think about, what are progressive steps that you could do to make a more resilient infrastructure. Oh, and not just infrastructure, but just the whole business and the business model. And it's the applicability carries over, even if it hasn't been scientifically proven yet. But carries over also into some of the business aspects. But with that said, so welcome, Barry. I'm really happy that we made this happen. What is this very, very basic version of what is residuality theory? Then how you got to this, and then we can do a deep dive and go much deeper.
So residuality theory is, I've come to realize over the last few years, it's a terrible name for any kind of theory. And I've been told by Matthias at DDD Europe that the residuality theory sounds like a chemistry textbook, and it doesn't really capture the imaginations of developers. But it's an idea that has been 10 years in the making. It has been 10 years now since the first kind of shots were fired in this work. And it started off with a project when I was sitting as the sort of global lead for the solutions architecture community at Microsoft. And I was given the job of training architects. How do we turn technically very gifted people into architects very, very quickly? Because we're in a bit of a hurry. And that led me to ask myself the question, what does it mean to architect a system? What is an architect? What makes me different than other people who have the title architect? Why do they deliver in a different way? What is it that we actually do? What goes on in our heads? And a little bit of scraping at that subject made us realize that nobody knows. Nobody knows. Some people are good at this. Some people are bad at this. Some people don't think we should even do this. And we don't really get deep down into why. And I started to really critically think about what is it that happens in my head when I do a project, when I deliver something. How do I know that an architecture is right? Because it's not math, right? I can't prove that my architectures are right, but I still, on some level, know that I'm right most of the time. And I have some colleagues, and they know also we're right most of the time. We're senior architects. We build big stuff. And it works. And so I started scraping and saying, what is it that we do? And I started to discover that those of us who continually delivered on a good level were very, very critical thinkers, to the point where we would, almost all of us would have at some stage been described as being quite negative. And we would tend to, when you're designing a system, rather than saying, how should it work? I would tend towards what's going to break it? Something's going to go wrong. What is it? And I'd realized over time that I'd picked up this habit of stressing a system to the point of ridiculousness, saying this could break, this will break it, this will break. And I realized after a while I wasn't really that concerned with what's going to happen. I was more concerned with where are the fault lines in an architecture. Because when you build a structure, when you build an architecture, you have places where it will crack, you have places where it will break. Every architecture has crumple zones and fragile areas. And I realized that me and a lot of other senior architects over time basically were able to figure out that the key to successful architecture isn't in the designing of the beautiful cathedral with the perfect abstractions. It's about knowing where it cracks when stuff moves. Just like building architects in Japan know that the most important thing about the building we're building is where does it shake, where does it wobble, what cracks in an earthquake situation. And I started trying to formalize this, and I started digging around, inspired a little bit by Nassim Taleb's work, which seemed to be equally as negative in viewing the world as what I was. And then I went a few steps further and I started digging deeper and deeper into the complexity sciences. And I produced a couple of papers, which I published in some enterprise architecture journals, which kind of shook people up a little bit. And then eventually those were published academically because someone noticed the paper and said this deserves more than just an enterprise architecture journal. And that led me to saying, I'm going to do something different. So I started to speak at conferences. People started paying attention to the ideas, and I thought, I don't just want to be another IT guru, who goes around at conferences and talks about stuff. I want to really leave a mark here. So I thought, I'm going to go back to school. I'm going to turn this into a PhD project. I'm going to produce real solid research that shows that this idea either holds or doesn't hold. It doesn't really matter which. And kind of lead by example and show the world that, we don't have to just endlessly debate things. We can actually do some scientific work and show that this idea is good or bad. And over time, then the ideas got formalized into this thing called residuality theory. And the point of residuality theory is that if you look at all the other sciences, all the grown-up sciences, not like our little branch of madness. If you look at physicists, physicists have a unit. When they talk about the world, they have this unit. That unit is the atom. And then obviously Newton had his magical, invisible, non-existent, existent particles. That was the unit of their universe, and everything builds up from there. And a chemist will have the molecule, and a biologist has the cell. You go all the way back through the history of Western thinking. The ancient Greeks had earth, fire, wind, and water. Everyone has this unit that they build things up from. And that's how you then build a set of theories and ideas around this one concept. And if you look at software, you find that software has been on this tortuous journey trying to find what is our unit. What is the base unit of what we do? And we started off with the procedure. We started off with the machine and the card, and then the procedure, and then the module, and then the object, and then the component, and then the service. And somewhere we wandered off and said, no, it's the function, it's the function, or it's the feature, or it's the process. And we've tried dozens and dozens of different things. And if you're a software architect, there are three huge problems that you struggle to solve. One is time. Because you're drawing something that's static. Your architecture is static, but the real world that it lives in is not static. It's moving. Time is changing things. The second thing is change, because everything is changing over time. And the third thing that we don't capture is uncertainty, because we don't know what's going to change. And those three things are always there in the background of every architecture is weak. And every drawing that you say, this is my architecture, you've got a bunch of boxes with lines pointing between them, and you know that time, uncertainty, and change is going to crush that picture over time. And that's because we haven't got a unit that we can talk about. Physicists can talk about atoms, and they can talk about those atoms in the context of time, change, and uncertainty. An atom still holds over those three variations. And architecture doesn't. So we haven't got the right unit of software. And so the residue is designed kind of on purpose, kind of accidentally, to be the unit of software that survives through time change and uncertainty, so that we can talk about things in a way that's safe for us, so that we're not reduced into talking about a particular static moment in time, so that we're not building an architecture of a software system for a magical moment that doesn't actually exist in time and space. And that means, and the residue gives us that ability. And it also crosses very nicely with a negative attitude as well. So because what we talk about then is, what is this architecture? It's not just one static thing. And it's not a component, it's not a set of components. It's a collection of components in a particular stressful situation, in a particular collapse. And the residue is what's left over of the system at every particular collapse. And so what you end up with is a map of your system across many potential realities that all look a little bit different. You collect all these little differences. And there's a calculus reference in there as well somewhere. And then you integrate them all together and you get a singular architecture. And so the way that we think about software is no longer at the function or the component level, it's at the residue level. Is what does this thing look like when we break it? And when you do that, you can't avoid but find all the fracture lines in your architecture. That means when you put it into production, you get much less surprised by what actually happens. And what we end up doing is we produce architectures that are able to survive things that no one's designed them for. Which, when you say it like that, it sounds like some kind of miracle, but it turns out there's a very simple mathematical reason why it works. And once you figure out how simple it is, it becomes astonishing that it's taken us 60 years and no one's figured this out yet. And so the pattern that everyone missed is that the people who were really successful at this were all really negative. That was the starting point. Why are we also miserable? And that's led to a new way of thinking about software engineering.
Oh, so the story has changed a lot since I last heard it. It is really, really interesting to hear this extension. The building blocks. Can you make it a little bit more concrete? Because, people are probably now thinking like, so building blocks, but how do you go about this? Like, let's talk about giant fire-breathing lizards and how they help you to find your residues.
Yeah, so a residue then is just a system that has been damaged in some way. And so if I have a house, for example, let's use a real world example because it's easier for people. Let's say I have a house. I build my house and I called that original building my naive architecture because it's naive, because I just thought, I have a house. What are my functional needs? Well, I need some rooms and I need a kitchen and I need a door. Okay, all this basic requirements, all that stuff that we do, features. And we build this house and I think, good, now we have a house. But then it burns down. And I look at my house and I think, some of the decisions I made when I built this thing weren't very smart. You know, the way that I didn't have enough walls. I didn't have, if the walls between the kitchen where the fire probably started and the rest of the house, if they'd been built in a different way, the fire wouldn't have spread, things like that. If I'd had some fire alarms, maybe some fire extinguishers, then the residue, if your house burns down, the residue is just a bunch of ashes and black stuff and smoke and everything's gone. And so what you do then is you think about this in advance. You say, what kind of things could stress my house? And the one obvious thing is fire. And so, we're going to have a fire. Let's have some fireproof walls. The architecture starts to change a little bit when I think like this. Let's have some fire extinguishers. So you're adding some different things, maybe sprinklers if it's a commercial building. And also I've got some stuff that I don't absolutely, even if the house burns down, I want it to survive. And so you design a little safe. You put your stuff, your deeds and your money and all of that inside your little safe. And then you come up with another thing, another stressor that will will cause a different residue. There'll be a different set of lines, different set of fault lines along which your house can crack. And so flooding might be a different thing. And so you talk about flooding. What will flooding do? What's the residue if my house floods? And then you realize that the sprinkler system you put in might actually be the thing that causes your house to flood, and you might have an extra few steps. And you realize that this safe that I've designed is going to have to be on the second floor because it's not necessarily waterproof, and if the flood water comes in, I want to protect this stuff. And so your architecture changes again over time. And this is how when you sit in your house today, there's a whole bunch of this residual thinking that's informed the shape and the form and the way your house has been built and all the regulations that the builders probably sort of half followed when they built your house. And that's how we've done this residual thing. And that's time and change and uncertainty gets baked in. And the real architects, people who build houses, they've had thousands of years to build this set of residues and understand it. As software engineers, we don't get that luxury. Our industry is only 60 years old, and every project that we build is kind of unique, because every house is being built on new ground with new materials and new ideas and new things. And then, of course, you can have other kinds of stressors. Someone comes along, buys your house, and they say, well, we don't want it to be a house. We want it to be a fish and chip shop. And then you've got to rebuild, and the whole fire thing becomes very different, and people have got to come in, and the driveway's got to be changed. And that's a very simple explanation of what residuality theory actually is. It's a very practical example of what the developer or the architect actually has to do. Underneath that, there's a bunch of theory, and the theory comes from the complexity sciences around something called attractor networks, which is a theory that any complex system will have endless trillions of potential states. But in reality, we'll only ever see a few hundred or a few thousand of those potential states because they all limit each other and constrain each other in some way because they're so complex. And it's a theory called of attractor networks, which was developed by a guy called Kaufman in the 60s. And this is an explanation for how all complex systems work. So economic, biological systems all follow these rules of attractors. And a house also follows a bunch of rules. There's a bunch of attractors that you see houses fall into all the time. They can burn down, they can get flooded, they can sink, they can crumble, they can rot, they can get damp, all of these things. And so investigating this space of attractors is what we're doing from a complexity science perspective. And that's something that we're not very good at in our industry yet, because we're always been focused on just this one attractor, which is how is it going to work functionally. That's just one tiny little slice of what an architecture has to do. It's 100% of what a developer has to do, make it function, make it do this, but it's a tiny percentage of what an architect has to think about. What way? And so we then take the job of saying, how does this thing fall apart? It's my job as an architect, I believe, to make sure that things fall apart in a way that's kind of graceful, rather than a surprise, because that's what gets us into trouble as software engineers. Not when things fall apart, because they will always fall apart. It's when they fall apart in a way that's not elegant and not predictable, and it feels like it's out of control.
Or like that's the whole thing just crumbles apart, and that instead of like a small piece falling apart, there's like a chain reaction, and everything just fails.
Exactly. And no one's prepared for it. No one knew it was there. And it also goes back to the problem that I said about time, uncertainty, and change. Well, the biggest challenge of software architecture is that we have to build structure in our code. And that structure, once we built it, is fairly fixed. You can make it a little bit flexible, but it's fairly fixed. There's considerable effort in changing the structure of a software system, even if we sometimes think that it's not. This difficulty in changing things is that when we try to gather requirements or risks, we sometimes don't admit to ourselves that we don't know what's going to happen in the future. As an architect, the reason there's so much uncertainty is because we're building for a future, we're imagining a future that no one else has imagined yet. And if you're running a business, if you're just a business person, you can just deal with the future as it turns up, and you can make decisions. Say, we're going to change this, we're going to change that. But if you've already put that into a structure, a software structure, then you've already made decisions about what this thing is going to do in the future, but you might not even be aware of them. And that's what makes our job terrible. So that's what makes it difficult. That's why we should get paid more as architects. And this is the big challenge. And sometimes we get so caught up in a particular solution. Maybe we're going to say, hey, continuous delivery or continuous integration or Kubernetes will solve all of our problems. And then we focus on making sure that we have these things in place. And then we realize after a few years and we get disappointed, don't we? Because all our problems haven't been solved. In fact, we might have made them worse in some cases, and we haven't solved them. And it's because the real problem at the heart of architecture is this continuous change in the environment that we're building in. And we're using traditional engineering methods to do that. And traditional engineering methods are brilliant for traditional engineering and also for some aspects of software engineering. But what we're doing is not traditional in any sense of the world. So if you imagine an aeronautical engineer having to build aeroplanes in conditions where gravity and the properties of aluminium are constantly changing, then that would be a completely different job with a completely different set of skills and ideas. But we've taken their tools, because that's all we had as a point of reference, and we've brought them into our industry, and they just don't work. And that's why we've been having so many issues with defining software. What is software architecture? That's why that argument has been going on for 40, 50 years, and no one still really knows. And the uncertainty is very, very central to that.
For me, there's so many parallels with strategy, like business strategy, because business strategy, I was recently re-listening to Good Strategy, Bad Strategy, and it's from Richard Rumelt, which I think is brilliant. He talks about it, how a lot of organizations are doing this terrible strategy where they're just saying like, well, it looks like this thing is working for other companies, so let's also do that. Or it looks like their APIs is now a pattern that we should all be doing, so let's do APIs. And I think this is more or less also what you're encountering in the architecture scene, is that people are just kind of like tactics parrots or tactical parrots that are just trying to replicate what other people are doing for the architecture, which not necessarily makes sense, because you need to build something that is going to address your specific position and like your level of resilience that you require in your business, depending on how much you can invest, and then also depending on what residues are actually important for your business. Is that a good characterization?
It is, yes. I think that a lot of senior business people, and this is the same with any aspect of complexity. When you talk about complexity, very senior business people will usually nod along and say, "Yeah, we know this already. This is how we act. This is how we act in the world. This is why we're senior business people. This is why we're still around." They're able to think in terms of residue. I think a really good example of that is if you look at where Microsoft were 10 years ago, where they were failing, or maybe it's more than 10 years. It is more than 10 years ago because I'm old. 12 years, 13 years ago, Microsoft were taking some heat for doing some things that weren't very good. Windows Phone was one of them, and Windows 8 was another one of them. And these things weren't very good. But at a senior level, they weren't doing Windows Phone and failing or Windows 8 and failing. They were doing Windows Phone, they were doing Windows 8, they were doing their Windows Server business, they were doing Office, and they were doing this thing called Azure, which at that time was still fairly small. And at the end of the day, some of those things crashed and burned. Right? The building fell down, the house caught on fire, especially for Windows Phone. But look at what Azure is now. They had enough residue in place. Their strategy was broad enough to be able to cope with the fact that some of this, not all of this, is ever going to fail. There are going to be bits of this that fall apart, and that's okay, because if we have enough of them, enough residue, enough stuff, then something will play out, and it has played out fantastically for them. Their share price, despite the disasters of Windows Phone and Windows 8, their share price is now 8 times what it was when I left the company. I think 12 times what it was whenever it was bad, and that is so you see these ideas turn up again and again and again. When you're working with things like business strategy, it's a little bit fluffier. And when you're working with software engineering, so there are mathematical rules that allow us to leverage them all the time, and that's only because software is so rigid. In business strategy with markets and things like that, there is no rigidity that I've seen. And so while the ideas seem to apply in a common sense way, they're not guaranteed. And you see that in business because nothing's guaranteed. But you can more or less guarantee that an architecture is going to be successful.
Yeah. And when you talk about these different residues that Microsoft set up, you're not just talking about having like multiple bets. You're talking about different components that are interacting with each other, that are together forming products. Where different pieces can fall apart, and then still you have good outcomes that still come out of it.
Yes, right? Yes, exactly. So a lot of the people who were involved in those efforts that didn't go so well, they didn't lose their jobs. They're somewhere in Azure now, making money and being happy and stuff, and trying to forget Windows Phone. It's not that you separate things out and do lots and lots of different things. It's that everything is interconnected and moving, and you have to think about the whole. And that is what we do with this theory, with our architectures.
The thing that really sparked my fascination is this idea of designing for the worst possible thing that can happen, and then just one or two residues will fail, and then the rest will still stay working. And because of that, it becomes much easier to recover from that failure, because you don't have like the whole thing going down. And then also that careful balance that you help to create with your practice between, because you can just go full microservice, but that does not necessarily mean that actually you are going to be more resilient. You might actually end up with something that's even more fragile. So it's not simply about just cutting everything into small pieces and then hope that does the job. It's really something else, right?
Yeah, so this goes back to the work of Kaufman in the 1960s, where he developed this thing called the NK model, where a system's, let's say, complexity, for the sake of simplicity, is a factor of the number of separate nodes or agents in that system and the number of connections between them. And when you build a software system, as a software engineer, as an architect, you're making hard decisions, like solid decisions about there will be this number of components and they will be connected in this way. And so one thing that you can do as a software engineer is you can say that we're going to keep it simple. N, the number of components, and K, the number of connections between them, is going to be very, very small. And you end up with a monolithic architecture. And we know that that's fragile. We know that when you hit a part of that architecture, everything's going to stop working because there's so few pieces. And you can you can swing to the other end of the pendulum, which is what we do in our industry. And you can say, no, N is going to be enormous. There's going to be K, the number of connections between our components, is going to be really big, and it's going to be called microservices. And the problem with that kind of architecture is that, sure, it's hard to knock out the whole architecture. But when you knock out one tiny little piece, it takes operations 3 weeks to figure out what happened. And what happens in that kind of architecture is it generally dies and collapses under its own weight. And you'll see this. You see this in biological systems as well. So Kaufman was a biologist, and he was interested in evolution. And you can have very simple systems, very simple creatures will tend to die off because it's easy to kill them because they don't have a great deal of moving parts, and very, very complex. Complicated things will fall apart much faster because of the collapse under the weight of managing themselves. And Kaufman came up with this idea that there's a line in the middle somewhere, a perfect optimum balance between the number of components and connections. And he calls the line the edge of chaos, which is something that management consultants have been running with ever since. So I don't think they really understand it a lot of the time. But a better term for it is something called criticality. And so a system has criticality when it's on this line. It has a perfect balance of N and K. Which means that you can't kill the system by just killing a few components. It will keep moving. But the job of managing that number of components and connections isn't so enormous that the system collapses in on itself. And this is what software engineering has been doing from the start, since we started working with modules, getting that right balance of module and connection. And this is where something like service orientation is a huge step towards helping us decide where are the lines between these components and how do we control the connections between them. Service orientation was probably the biggest step towards managing just that particular piece. And the whole API, the patterns and the idea around APIs, that is all about controlling N and K and getting it to the right level so that a system can survive in the long run. And that is criticality. And that's the job of an architect, is to deliver criticality. And that can be really confusing for us because a programmer's job is correctness. A programmer has to deliver something that's correct and passes a test, like a mathematician. And strangely enough, we've been taught by mathematicians. Computer science professors are just mathematicians. And we look for this correctness all the time. But the job of the architect is so different than correctness. It's criticality. And when you're delivering something that's critical, it means that it will survive even when things you don't know are going to happen. But it also means that you're going to be a little bit wrong a lot of the time because there's no correctness. And it's very, very difficult for us, especially because most of our architects come up through the ranks as developers. And getting people to let go of this idea that you have to be correct is really, really difficult. And getting to that line of criticality, that's all we have to do.
So this correctness, I've been thinking about this from the perspective that, with software, we're trying to make deterministic systems. that we can like completely predict that they're going to do exactly what we wanted them to do, like right when we started designing them, which is a really weird thing because it's really powerful because it gives us, I think that's what engineering is all about. It's like making something where you know that it's going to survive the circumstances for which it's built. But then if you throw a bunch of evolved monkeys into that doesn't work anymore because people start messing around and start doing unpredictable things, and then things start falling apart, or reality hits and things start falling apart. Now, one of the things that I've been looking at with the whole large language model renaissance, because it's not like they've just been invented, it's just that they've now gotten into the public eye. One of those things is that those things are not predictable. They're actually built to be like emergent and surprises and in what they're doing. Is this already changing some of the engineering mindsets that you're seeing in companies, or we're still too early for that?
Yeah, we're still too early for that. And when you ask that question, it makes me think that you've seen my talk on this. I gave a talk a few months ago called Unstable Diffusion. So one of the things that have happened to me in this journey is that I've gotten really deep into philosophy and why do software engineers think like this? Why do mathematicians think like this? And why is it not working in the modern world? And so one of the things I see happening with the advent of LLMs in our industry is that people are starting to ask philosophical questions, which is really cool. It's really good. Now, some of the copy-paste Silicon Valley thoughts on Western philosophy are quite frankly embarrassing, but at least we're taking a step forward. And one of the things that I talk about is that there's a bunch of patterns in LLMs and in broader machine learning as well, in not just generative AI, but also the old boring AI that actually does all the good work. There's a bunch of different ways of thinking in there. And a lot of them are connected to the ideas of complexity and network science. What I've said in this talk is in 10 years' time, the way that architects think will be different because we have been thinking along these lines, which is called technical rationality, which was named by Donald Chern in the 1980s. And the architects have been acting in the belief that the world is knowable and deterministic, and if we just get a process and execute on that process, then we've done architecture, and that's why you get nonsense like TOGAF coming out. But with the LLMs and with machine learning patterns and the things that are happening like stable diffusion, where you feed noise into a system, so that idea of technical rationality led to executing architecture in a very stiff way, as if the world was deterministic. With LLMs, people are starting to realize that now determinism might not be a guarantee in the world around us, and they're starting to become more and more aware of that. And a lot of the patterns that we see being engaged with through machine learning and LLMs are things that are quite alien to architects in terms of maybe we don't get the same answer every single time. Or maybe we don't need to have a perfectly described process about how to get from a problem to a solution. Maybe we can just bounce through it, take the best answer that there is, and work forward from there. And so a lot of the patterns, I believe, that are turning up in LLMs, and what I actually say in this talk is that the impact on architecture and how software engineers think might be a bigger impact than the LLMs themselves have in the long run on our industry, because I kind of see them as a little toy that'll go away in a year or two, but it might change our thinking as an industry forever. And I think that's a good thing, because those ideas are way left field compared to what traditional engineering was. And that's why it seems like magic, because it's not technically rational. So if you feed images into a system and distort them a little bit every time, eventually you can produce brand new images. That's bizarre from the perspective of technical rationality. But if you think about how we take requirements over and over and over again through a project with slightly different tilt on them every single time and then end up producing an architecture, it's not really that alien to us. And so I think that's kind of exciting. That talk hasn't been recorded yet, but it will be in May.
Okay. So, I'm very much looking forward to that.
So there's a lot of of course, because that's what I like to do. A lot of contrarian takes in that. To say maybe the future of AI isn't all sunshine and rainbows and unicorns, but there are lots of really interesting things happening on a philosophical level that might change how we do architecture.
Yeah, and this comes back to the piece that we just started touching on a little bit before we started recording. This idea of, well, I've been talking about APIs as not products, but as a utility. But when I say utility, I mean something like streaming water or electricity, which is, so it's not the economical sense, because a lot of people, when they hear utility, they think in economical terms. Similar with commodity, they think in economical terms, like something where there's no more margin. But that's not what I'm talking about. I'm talking about a networked, ubiquitous technology that is transforming how the world works. And if we want to build this almost like a magic, it's almost like a magic enabling layer over the whole world, where you can go in a room and then say a magic word and suddenly the light goes on and stuff like that. We need a different way of doing architecture and doing software that's much more resilient, that is not built for a single purpose, but that is providing these capabilities so that people can like play around with them and do unpredictable things that are making their life easier and that are enabling them. The way I think, or I started thinking about APIs is as a sort of like a utility for digital interfaces that is enabling us to build currently to handcraft these digital interfaces. And here, I'm not sure. It might be that it's not going to happen, but I imagine that the LLM story actually might enable us to do things where regular people can just use normal informal speech and have actions happening through a digital interface. That's the piece that I've been working on, and I love to hear what you think about that. Well, this unstable diffusion perspective and also from a residuality perspective.
So I remember once in I think 2016, I was working with an integration team at a large company, and so it was very API centric. So they were hosting many APIs, and we were hosting them in a very organized, very structured, very beautiful way, in a way, and it was pretty good what they'd done. And they were facing some resistance from agile teams who did not like the fact that if we want to build and deploy and run an API, we have to get permission from this central team so that we don't do anything stupid in terms of security or duplicity and things like that. And so there was an internal war going on. And so they brought me in and said, tell us what the future is. And I so of course I say, well, no one knows the future. That's my thing. But I said, look, this is a potential thing that I can see happening. And I drew a little map, and I said, as we move towards 2025, the work that we do, where you sit down and you decide on the schema and the structure of an API, will start to disappear, because what you will do is that someone will throw a bunch of garbled text from a client at your API, and there'll be a little ML node that sits in front of the API, looks at your garbage, and figures out what you want. And I said, we're not far away from being able to do that. And then over the years, I thought, God, that was nonsense, what I said, because we're not even moving slightly towards that. And then at the end of 2022, just boom,
yes.
Here. Yes, and it's looking pretty good for 2025. You're going to see the first API tools where you can throw. Initially, my thought was that you don't need to be as strict. When you define a schema, if I throw a message at a web API that says a television and a credit card number and a product number, just figure it out. I want to buy it. But obviously, if you look at the advances that are happening with LLMs, then maybe that will just be, I'll speak to it. I say I'd like one of these kind of thing, and I can definitely see that API definition, schema definition, is something that won't be as rigid and as stressful as it is in the future, and that's going to give us a lot of flexibility. That's going to give us a great degree of resilience. of course, when I said this, it made that integration team incredibly upset.
So which is a good stressor to see how, and having no overlaps and being fairly disciplined in your design. I'm not sure if that is going to go away necessarily. Thinking from the three economies perspective from J. Bloom.
Yeah.
The middle one, the scope. So APIs definitely are economy of scope. So the more they get used, the better they become. So they're one of those types of assets. So I think that to be able to create as much reuse as possible, you need to do some. Yeah, you need to have some discipline, I think. Or do you disagree with that, or how do you see that?
I don't know yet. I don't know. I think that there will be a spread. There will be certain use cases where we see where discipline stops being a thing, where you say, look, we don't need to perfectly define what's going to come in. If something comes in and we can make sense out of it, then we'll do something. And if something comes in and we can't make sense out of it, we'll just bounce it back and say, what? and that will be okay. Now, obviously, if you're running a bank, that's not okay. You're still going to need discipline, right? You can't say, we think we should take 100 euros out of this account and put them. No, we can't do that. So there will still be some discipline. But there'll be room for flexibility, perhaps, in in our APIs, which today is a kind of painful schema update.
Yeah,
it becomes on the fly processing of something slightly unexpected in some use cases, and it'll be interesting to see if we can do that in a way that's affordable as well. I mean, it's cool as technology people to do that, right? But is it cheap? Can we afford the electricity bill if we do it this way?
So I think one of the I'm curious about your idea about this. One of the things, and actually I start seeing it happening actually in reality already today, is that instead of competing on API design, which is currently happening, because I have the best API, so you should work with me instead of the others, and then you're locked in because you've now built an integration for my API, and you have to refactor everything if you want to work with somebody else. That this is going to go away, and that we start seeing more standardization of designs in certain pockets of the industry. I see this already happening in banking. PSD3, this is coming. Also in the telco sector, this is happening with Camara APIs. GSMA is doing things like with Mac and stuff, which is standardized API designs that they're all applying across the industry. So I think some of this is going to happen, which means that you'll just take the design that's out there, and then the differentiation will be in how well you're delivering your services and how good you're at marketing them, rather than and then maybe some network effects with other stuff that you're providing. But rather than right now, we're in this weird world where we're competing on who has the best API.
Yeah.
And I think that will change. So from that perspective, I guess I agree with what you're saying, that it's going to be less important.
Yeah.
But I'm not sure if it's going to be less important because we've already standardized a lot of them.
Yeah.
And that's the affordances, because this was something another guest of the podcast, Marsh Gardner, mentioned, and it really made me think, was that great API design is entangled with the affordances that the API provides. And that's really interesting. And also, an LLM can't do anything with your API if you're using cryptic words that don't mean anything.
Yeah.
Fascinating, really, really fascinating. This is really, so much is going to change.
Yeah, there's so much happening right now. There's a lot of emphasis on these RAG patterns where companies are internally training models so that the models are getting weights that are based on the internal documentation of the company instead of the external world, which might lead to a condition where you get sensible answers from the LLM that are in the context of that business and weighted the right way. But there's huge assumptions there, obviously, that your documentation reflects how you think, which may not necessarily be the case.
And that is consistent.
Yeah,
That's normally not the case.
Yeah, and that comes down, I think, to the thing with affordances that you're talking about. If it's inconsistent, I mean, where does that leave us? Does that leave us with what's the next step? What's the next thing that becomes possible when we can solve 80% of our cases in a way that's very flexible and very simple, and 20% of the cases turn out results that are kind of weird and crazy? Because that's more what real life looks like as well.
Yeah.
And so it'll be really interesting to see what happens over the next couple of years. And if, there's so many different ways it could go. It could all snap back to standard and perhaps even more focus on standardization and rigor after some hallucinations trigger a market collapse or something like that. I mean, that's definitely going to happen at some point.
Yeah. So we're doing this conference, AI the Docs, where we're going to invite people to come and talk about what's the real life applications already that you can do with this stuff. So the thing that I've been telling people is like, okay, so if you're really big, then maybe you should go play around with some internal models. But otherwise, probably one of the best things to do is just to get ready for it and just make sure that you have the foundations that can be used by these systems to do interesting things, like get APIs so that you could then put an LLM on top of it so that people can start asking questions to your backends and stuff like that. Make sure that you have security in place so that you can make sure that nothing bad happens from those questions. Get good documentation so that you can then use that for training systems. So that kind of stuff. But it's AI readiness instead of like actually really diving deep.
I think when you get to these situations where lots of things are happening, and your system maybe isn't as rigid or as predictable as it was in the past, and lots of different things can happen, then the concept of correctness is something that you're saying, I'm prepared to give this up. It's okay in this particular business case to give up correctness. And when you give up correctness, you have to have criticality, because you can't just let things collapse when it's incorrect. And that's when something like residuality comes in to back you up in that kind of case, because the old traditional rigid methods of engineering just aren't going to have anything to say to this kind of outcome, because if the outcome isn't rigid and structured, then why on earth would the process be so in order to deliver it? It becomes stranger and stranger, this future.
That just sparks a bunch of ideas about like what are the residues that are being fed into the LLM that might be your interface and like that are working in the background. But it also makes me think about how do you make sure that a novice user, like you have a trainee that's asking questions to your LLM and is like, this must be true, and goes and really messes up things, how that is going to, like how you can count that into. Have you actually done any research now on if residuality also applies to like the more human systems? Is it still only in software?
I'm still focusing on software because there's this lovely mathematical leverage that makes it empirically provable. And so I have looked at some other things, but I got told off. And my professor said, one PhD at a time. You don't need to do any more. I know that there are some people in the world out there who are interested in these ideas, and they're taking them into different domains. And that's really interesting. I say the same thing to all of them: is be careful. Just because it works in software, just because I've shown that it can work in software, and that there's a mathematical underpinning to it, doesn't mean that it's going to work in the real world. And the rule, so when we work with a software system, it's a rigid, structured system, and it has a much lower number of potential attractors than the system that it lives inside, which is the business and the social system. And the difference between those two numbers is what makes it possible for us to say that we can definitely deliver good architectures using these ideas. But when you take something that's also has a huge NK number and a huge number of potential attractors and put it inside a system which is probably bigger, but we can't prove it, then the mathematical leverage disappears. And what you end up doing is you're actually applying human common sense, but you think that you're safe because you have this scientific framework, and there's a danger in that. Which is why I warn people before they get involved in sort of social research, social science research around these ideas, around team structure and things like that, to be very, very careful that you're not leaning on an assumption that's based on a complicated system inside a complex system, because a complex system inside another complex system, anything can happen. But I haven't thought enough about that to completely rule it out, because it seems from a common sense perspective that this should work.
So, like, I think for businesses, it feels to me that it must work, because there's also not that many attractors for businesses. You're failing or you're succeeding, and then there's different forms of succeeding. There's different parts of your business that could be failing. I think because there's the mathematical rigor of finance that you have to apply. If you're a business, there's no other way. Like if you're too long unprofitable, then you're going to fail. Maybe that there it does apply.
The thing about businesses is that we expect them to fail. Most businesses fail,
right.
And that's okay. And you go, oh, whoops, I'm an entrepreneur. I crashed 5 times before I had a sustainable business, and that's okay. If you're a software architect, you don't get that grace. Right? You don't get that. Oh, you don't get to go, whoops, the whole thing came crashing down. It's over. And that's why we have to think about it in a slightly different way. An architect who crashes 5 projects in a row is going to be an unemployed architect, or should be an unemployed architect.
Yeah, but isn't this a Silicon Valley way of entrepreneurship, where you're shooting for the moon, and if you don't reach the moon, then next time? Yeah. Because like if you're self-funded, you don't want to crash and burn.
No.
Like
Yeah, I guess, yeah. But many still do. I mean, if you look at the restaurant industry, crashing is a very high probability for a new restaurant that's opening.
But isn't there also then a need for a residuality for businesses? Because there's ways to build a restaurant that is resilient.
Yes, and obviously, I mean, the very common sense rules, like don't mortgage your house,
or start with a food truck.
Yeah, something, sort of things that seem common sense, that you seem that actually parries with residuality.
Yeah.
Sometimes I can look at the behavior of certain governments, like the British government and Brexit, and say, if you guys knew about residuality, maybe you wouldn't have gone down this path. One of the things I think that kind of shocked me was, on social media was suddenly seeing an uptick in the number of people who were following me who had military backgrounds.
Interesting.
And it's like, well, what do you want? and then realize that, okay, this is a very natural.
Doesn't make sense.
It's going to appeal to someone who's in that kind of a situation, and in military situations. Everything's on fire. Unexpected stuff has happened. How do we plan for this? And I thought, well, it's obviously has some transference to the kind of problems that they're trying to solve. And again, I'm still very cautious and say, look, I know this works for software, but we need to be careful that we don't assume that it works everywhere else. Kind of like, the Spotify model in the software industry. Everyone looks at Spotify and says, well, they're making money, so this must work. And then it crashes and burns everywhere else, to the point where the Spotify people have to get on a stage and say, will you all please stop? Just because it worked once at Spotify doesn't mean it's going to transfer to all these different things.
By now, it's changed completely. And what you're talking about, the Spotify model, is no longer what we're doing here in-house.
Yeah. When I'm teaching the courses, one of the last things I say to people is the unfortunate truth of our industry is that even with these ideas, which make it much easier to survive and understand complex environments, you're still going to have to sit down and think very, very deeply. Every time you do something, it's never going to be easy, and it's never going to be a quick answer or a silver bullet. You're still going to have these tools, and a lot of the tools that I teach that are based on residuality are meant to trigger thinking rather than solving the problem. And so that we get to this point of criticality, which is the goal, I think, of any and all architecture work.
I just was thinking, like, I think another industry that would be really, really interesting for these ideas is like investment portfolios. There's already this idea of diversification, but that is just like spray and pray. But I think really thinking about it from a residuality perspective would make more sense.
I think that work's already been done by a guy called Mark Spitznagel in the United States, who's written a book which I bought, but I haven't completely read. He's been running an investment fund that's had incredible results, and it's very much It's very, very close to the thinking of Nassim Taleb. So there's some crossover between the thinking there, and it's based on the idea that there is going to stuff is going to happen that we don't have control over. It's going to happen all the time, and it's your black swan theory basically, applied to investment banking. And those ideas are very, very close to the idea of residuality.
That's the idea of having like a layer in your architecture that is allowed to fail, like the how do you call it, anti-fragility.
Yeah.
But it's not fully residuality yet, because residuality tells you also about the interaction between the components. And I think anti-fragility is more like you should have a layer that can fail. And and you just have enough pieces in it so that you're definitely going to be okay sitting behind that.
Yeah, so anti-fragility is there's a whole chapter in the book that says don't trust geeks, don't let the technology people come because they will destroy everything, and that's why residuality had to take a slightly different direction and say actually we can do things with our technology that allows us to survive in a world where we don't really know what's going to happen, and that's very much the root of it. Then Taleb's work after that goes very deep into probability. And I went down those rabbit holes and haven't found anything there that helps us really. But if you're working with markets and data, then obviously it's mathematically manipulable. The book is called Safe Haven: Investing for Financial Storms by Mark Spitznagel.
Okay.
Or Spitznagel, the Americans might say. It's a very interesting set of ideas that. And very similar. It's saying that eventually everything's going to fall apart, and you need to be ready for it.
But I think. Well, I guess the difference is that when you're investing in a portfolio, you don't have control over the companies that are in your portfolio normally.
Yeah.
And that's different with software systems, because you have, as an architect, you can change the makeup of the residues.
Yeah, so, you can.
Yeah. So I think with software, with investment portfolios, you're just hoping that some of them will keep standing.
Yeah. And they are also complex systems within complex systems.
Yeah.
Because the price of a particular share is the product of so many variables that it's simply not calculable.
Yeah.
And so when you're looking at a portfolio is a complex system executing within a complex system, which is an entire market, whereas software is, luckily for us, stiff and rigid and controllable, and we can control it. Like you say, you can't go in and control the share price or a particular business or how it reacts in the market. But and that's the thing that when I talk about residues, the basic lesson is that we as architects, we can't map or describe the environment that we're working in. It's too big. Mm-hmm. We can't predict what's going to happen in the future. The only thing we can control is the residue, how the system falls apart. Yeah. And we have complete control over that as architects most of the time, unless you buy in SaaS systems, where another architect's already made those decisions for you. And we have control. Yeah. And that's what makes this doable. A lot of the other stuff you'll see about complexity is you're working with a business or a team structure, an org structure, or a behavior of a certain group of people. It's a complex system within a complex system. Yeah. And then I see a lot of risk in being very defined and very definite about how things are going to work. Yeah. And you get some strange ideas like nudging. The way to change this system is to shame everyone into behaving in a particular way, and things like that. And it's like there's a really interesting paper came out on Twitter yesterday. But it didn't come out on Twitter. I heard about it on Twitter, is what I mean to say. It came out in a very prestigious academic journal, and it was a law paper, and it's a paper by someone called Megan Stevenson. It's called Cause, Effect, and the Structure of the Social World. And it's absolutely fantastic paper that says that, look, if you look at the kind of scientific research that has been done on kind of criminal justice programs, and that is a complex system within a complex system, they don't actually work.
Yeah.
And everything that we try to do inside these systems, even if we have a good theoretical basis or a good argument or a good political drive behind it, we're not actually changing anything in what we do. And I think that's a major lesson for us. I think it's a phenomenal paper. Not enough people are reading it. And one of the problems we have in our society, but especially within software, is the idea that this thing will work because I've argued well for it, or because this person who talked about it sounded like they knew what they were talking about. And that's why one of the reasons I decided to turn my project into a research project, so that if my ideas were wrong, I would have to come out at the end and say, I was wrong and you shouldn't do this.
Yeah.
And I think that's and within medicine, if you don't do that, if you just say my ideas are right and you try to sell your ideas with charisma, you'll quite rightly be labeled as a quack or a lunatic. But in software, you're a guru. And that's really, really dangerous. And I think that's something that we need to become much more aware of. And that becomes we become even more susceptible to that kind of risk when we're dealing with these complex systems within the wider complex environment. At least software is nice and rigid. I mean, the processor will not change its mind.
It's interesting because it's almost like a skeletal or like a scaffold for society that is like turning parts. There's some bad things also, right? Like when my daughter was born, her family name in Hungary could not be in two separate words because the software system does not accept two words, and that caused all kinds of problems. Like similarly, we're living in a street with a ridiculously long name, and some software systems just don't have enough characters. And then you get all kinds of problems.
As an Irish person in Northern Europe, most software systems and most government systems in Northern Europe assume that the apostrophe in my name is an SQL injection attack. So there's a lot of things take much longer than they should do. I understand that. Yeah, absolutely.
They're enabling constraints, but they're also like nudging us into a certain direction. But it's interesting. What will happen with this? Are we going to keep software as this temple of engineering, or is it going to become just like all the rest, like a bit of a hodgepodge of some structural, some more rigid things and less rigid things? It's going to be really fascinating to look and to see.
I was talking about this last night actually with some friends, and I think that one of the things that I'm hoping for, and this might just say more about what I hope for than about what's actually going to happen in reality, is that software will very soon lose its glamour, and the Silicon Valley thing will go away, and we'll become more like professionals who know what we're doing. And there's no glitz and glamour. We'll be like the structural engineers who make ventilation work in big buildings. Everyone is thankful that we exist because they can breathe, but they don't really know how it works, and it just works, right? And we'll become much more professional. But I think we have a journey to go, and hopefully residuality is a part of that journey, where we move from the ideas of traditional engineering to a new kind of engineering with a little bit more rigor, but and a lot more honesty about what we can be rigorous about and what we can't.
But I think part of this illness is this belief in anti-fragility. And there's this, the VC way of building businesses. You just it doesn't matter if 80% fails. You just need one that's going to become 20x, and you're fine. If we can prove, I don't know if it's even possible, but if we can validate, I feel that residuality is one step further in that journey, because it's not just something will succeed if you have enough pieces. Like it's similar how we started with the story about Microsoft. A really good architecture is not just I have a portfolio of products and one of them will succeed. A really good architecture is I have a bunch of reusable components that are residuals that will keep on working, and I'm recombining them into a bunch of different products that help me to make as many bets as I possibly can. and some of it will work. But even if a whole bunch of things don't work, I don't have to throw away everything, because I can then reuse those components to do something interesting again.
Exactly. And if simple redundancy or simple diversity already worked, we'd have figured that out already.
Yes.
I mean, we already tried that and it didn't work. And it's because of the interconnectedness of our components that simple redundancy and simple diversity don't work for us. And that's why you need the concept of the residue, which touches on the actual complexity of the underlying system. Absolutely. I think that the Silicon Valley way of doing things works in Silicon Valley. But if I'm writing a software system for a nuclear power station, I can't have that attitude. Or even if I'm writing the software system for the transfer of social benefit payments within a European country, I can't take that "it might work" or "it might not" attitude.
Even for IoT, it doesn't work. This whole Internet of bleep. That is basically a proof that this is just not sustainable. You cannot keep burning people out with, come in with a big promise and then crash and burn everything. I think this transformation from maybe like looking at the API patterns that we had, like the initial SOAP architecture, which was everything so connected that it became so rigid that nothing could change anymore. It just didn't work, to this RESTful architecture that is much more modular and it's just like whatever works in your small context is going to be fine, and we'll figure out a way how to connect it with the rest of the systems. Like maybe what we're working on really is like, what is then the next thing, which is somewhere in between, maybe at criticality between these two edges of architecture.
Yeah, it's strange that comes up, because I've had that journey from the first sort of SOAP services back in the very early 2000s through REST, and then I eventually hit IoT. And IoT, real IoT, where you're actually doing things, not just the PowerPoints and stuff that people were selling, but real IoT, when you're connecting millions of devices, pumping a lot of data. A lot of the ideas that we had about how APIs should be built and how they should work and how they should be hosted, it all just blew up. And so most IoT projects for me started as we had this traditional API approach, and we got to a few thousand devices and everything fell apart. And so a lot of these ideas I started to formulate from that journey through IoT, because it really tests an architecture. And what we've seen were these older SOAP and REST applications being stressed to the point of just burning up as you started to attach more and more devices and more streams of data and more uses for that data and more. And then suddenly the devices would change and all the contracts would change, but you have to support 5 different contracts for the same thing. And all of these old ideas, if you go back to the sort of Thomas Earl view on SOA and APIs, it was amazing to just watch how quickly things fell apart. And that's how I started to put these ideas together. So we need to protect ourselves, not just from what's happening now, but the next wave is going to break everything we thought was true today. And you might start to see that happen as these IoT systems then come into a world where you have this LLM approach to contracts, for example. That's and that becomes interesting then. And then you need something like residuality, because time change and uncertainty become the defining features of the architecture.
Yeah, because otherwise, like your ventilation will stop working, your lights will stop working, and like everything just because like when I said IoT, I meant this part, the home appliances. There's like, oh, don't you worry, your pretty little minds. Like we've got an app. you can turn on your stuff using our app. And then like, okay, well, what if you stop maintaining your app? Like when you're tired of doing security updates, then what happens? Like that 5,000 euro device stops working, and I think we just generally need this kind of mindset. The tricky thing is it's so easy to just have this throwaway culture. And because customers are idiots and they'll pay for it again. It doesn't keep working. We have to go, like, we need something better than that.
Yeah, one of the things I've been thinking about the LLMs is that this is probably our last chance, because we did this with IoT and we said, look what's going to happen, and it didn't.
Yeah.
And we did it with blockchain and absolutely nothing happened. And now we're doing it again, and I don't think they're going to let us have another go at this. Eventually we will be the industry that cried wolf.
Yeah.
It's like, oh yeah, sure, you're going to change the world again.
I think at the same time, we've already changed so much, because if you think about it, like mobile phones, that's all APIs. Like it's under the hood. That's just basically a bunch of context windows that are operating through APIs, and just that is actually magical already. It's just we get accustomed to a lot of really fast. but there are certain aspects that really are ugly, and that we need to do something about. Very much. I love this conversation, and I'm really happy that we could like dig a little bit deeper and like introduce people to the core concepts, but then also like play around a little bit at the edges. It was brilliant to have you as our guest. Thank you very much for the work that you're doing. It's fascinating and exhilarating.
Cool. Good to hear. Thank you for having me, Kristof.
Is there something that you can pitch already today? Like if people want to check out your work, where should they go?
They should follow me on Twitter, because everything that I'm doing is published there. I'm turning up all over Europe at conferences and running workshops. I'm doing a lot in Belgium. I'll be back in Brussels teaching a course in September or October, and I'll be if you have people listening in Hungary, I'll be in Budapest at something called Craft Conference in May. But if you keep an eye on my Twitter, I'm all over the place at the minute. And any eventual book will be loudly broadcast from that account, that it exists and can be bought.
Thank you very much, Barry.
Thank you.
Was lovely.
Thanks. Talk soon.
That's it for this episode. This episode of the Resilience Podcast was brought to you by Pronovix. You can learn more about our company at pronovix.com. And thank you for listening. And until next week,